Hello, we are the open source hardware enterprise of Michigan Tech. In this presentation, we will be going in depth with our project work for the past academic year for Design Expo 2020. The Open Source Hardware Enterprise is a student-organized and student-led program. Our current leadership is I, Zach Arnold, as the president, Lucas Butler as the vice president, and Dr. Pierce as our faculty advisor. Our team currently consists of 19 members of various engineering disciplines. The enterprise develops open source hardware solutions to address the problems of not only our project partners, but the needs of our open source community as well, while sharing the solutions and project details to the commons to grow the community's knowledge base. Our team currently has 5 projects being developed: Grobot, Fused Particle Fabrication Toolhead, 3D Printer Automation, Industrial Recyclebot V2, and LaserSor. Hello, I am Zach Arnold, and I will be presenting on behalf of the OSHE Grobot team, which consists of myself, Russell, Joaquin, Wilson, Erica, and Drew. The Grobot is an open source robotic platform which can be used to house a large array of sensors. Our application for the platform is to automate personal gardens. This robotic platform attempts to cut down on the time and effort people put into tending to home gardens. The platform can also be used to automate simple processes for other use cases. The robotic platform is operated by a Raspberry Pi 4 that controls 2 O-drive motors and interfaces with a variety of sensors. The drive system is powered by a 6S LiPo battery that is stepped down to 5 volts for control power. The robot is also equipped with a battery voltage sensor to monitor the battery level. Guidance for the robot is achieved through a wire following system using a frequency-induced wire and 2 inductors on the robot to locate the wire. To monitor the environment around the robot, we have added a soil sensor, a 9 degrees of freedom sensor to detect rollovers, an air quality sensor, a temperature sensor, and humidity sensor, as well as a webcam for visual updates. Here is a quick electrical system layout. The robot was designed in FreeCAD, which is an open source CAD package. The frame of the robot is built using 30-30 aluminum extrusion, held together with corner joints. This creates a sturdy skeleton to enclose the electronics and maintain a uniform center of mass. The axle assemblies are made custom with 3D printed parts using PETG, while the tires are printed using TPU. This allows for dampening in the chassis and allows for the user to make changes to the design of the tire tread to fit their desired terrain. The robot's web interface allows the sensor data to be stored in a database on the robot's Raspberry Pi and graphed out on the website. The website is built to work with both desktop and mobile devices so that the user can easily access their collected data on the fly. Here is a quick video of the Grobot moving.
Hello, my name is Jacob, and my capstone project this year was developing a fused particle fabrication toolhead, also known as a pellet extruder. During the fall semester, I was able to design and build my first prototype. After initial testing, I discovered that the toolhead was not able to extrude plastic. After further investigation into the problem, I determined the extrusion screw was the root cause to the problem. I decided to machine my own extrusion screw. To keep this project accessible, I used an angle grinder to machine the screw. In order to do this, I designed a machine to help control the angle grinder to be able to accurately produce an acceptable screw. This video shows the machine I designed to hold and position the angle grinder to cut threads into a steel rod, creating the extrusion screw. This jig uses belts and pulleys to link the rotation of the threaded rod to the rotation of the metal rod being machined. The threaded rod is used to move the angle grinder along the length of the screw being machined. By having the ability to adjust the parameters of the extrusion screw, this allows for more customization, which can hopefully help allow for a successful desktop pellet extruder. While my time this semester has run out to redesign a second version of the pellet extruder utilizing the in-house manufactured screws, the jig will go on to be published online so that way the open source community can build their own machines and manufacture their own screws. This will allow for rapid experimentation in order to optimize extrusion screws for desktop pellet extruders. In the future, we'll be working on designing a CNC version of the machine in order to manufacture screws without having to manually operate the machine. This would also allow for screw parameters to be changed without needing to change the hardware being used. As well, we'll be looking at scaling up the machine to make larger screws for filament extruders and industrial-sized pellet extruders. By manufacturing our own screws, we'll be greatly reducing the cost of both machines, as it is generally the single most expensive component.
Hello, my name is Lucas Butler, and I was the team lead for the 3D printing automation team this year. The goal of this project was to automate the 3D printing process, and in order to do that, we looked into multiple approaches this year, but we ended up settling on a simple one that would automatically scrape the print off the bed and start the next one in queue. We believe that this sort of system will help print farms and small maker spaces optimize their 3D printing process and help them get large batches of prints out their door. Some of the processes we looked into to try to automate the 3D printed process include a robotic arm and the automatic scraper design that we ended up settling on. We looked into a robotic arm made by Headington Dynamics named Dexter. We have this robotic arm in our lab, and we were able to use it previously to get small prints off the bed, but nothing consistent, as it was a complex system that was prone to breakdown. In the end, we ended up settling on the fact that the robotic arm was too expensive for most people to use, as well as overly complex for what we needed it to do. So we ended up using a 3D printed cart and rail system that would bring a scraper down to the bed and scrape the print off. This uses the Rambo control board already on the 3D printer. The mechanical breakdown is as follows. We have two motor mounts at the very bottom of the 3D printer and two lead-through catches at the top. And for the cart itself, we have a spring steel scraper and two scraper clamps on either side to hold it in place. And on the very end, we have a roller/lead screw receiver for the cart to move up and down on the Z-axis.
This is the Industrial RecycleBot version number 2. It is a redesign of an old project. Our goal is to recycle filament into a reusable spindle. Are we looking to cut costs, increase safety, and fully automate our system?
On the mechanical side of things, we increased the hopper size. We updated the design to accommodate more parts that are more readily accessible. We simplified the assembly and increased the barrel and auger size. We implemented the updated electronics using 3D printed housings, and we simplified the build process by making it more open source friendly. Then we also increased the safety of the RecycleBot by adding covers over the hot ends and the moving parts.
On the electrical side of things, we went with an Arduino Mega V3 for our control board, and we use a ramp 1.4 header for connecting to devices. The ramps board is originally designed for 3D printers, which gives us some useful functionality in addition to Arduino. We utilize a two-stage heating system on this with two heaters and individual temperature feedback for both. And our goal is to fit the majority of those components that aren't heat sensitive within a central control box, as well as avoiding custom circuitry.
For the software side, it's all controlled by a single Arduino. It has a maintaining the temperature feedback so we can make sure our temperature is perfect each time. We have multiple temperature settings for different types of filaments. Everything is automated on the spooling side, and it can be controlled via a Bluetooth app.
The Laser Saw is an open-source CNC laser cutter developed 9 years ago that uses a fixed laser with 3 mirrors to adjust the path of the laser into a focusing nozzle. Our Enterprise's laser cutter has been inoperable for 6 years and was due for a rebuild. To accomplish this, we compiled all the old documentation and looked at the key mechanical factors that led to operation failure. The solution we found was a redesign of the gantry's belt tensioning mechanism to prevent slipping and misalignment of the gantry, which would cause it to fall off the rails, resulting in a failure. This new design, which is similar to the tensioning mechanism used in an MP-CNC, which uses zip ties that can be adjusted to change the belt tension, was 3D printed and installed. The solution worked well in combination with straightening and squaring up the rails. We then began looking at the electrical wiring, which needed to be cleaned up with proper wire management techniques. In the middle of this process, we were interrupted by the COVID lockdown. We had plans to finish wiring, update the firmware configuration, recalibrate the mirror positions, and develop a standard operating procedure for the laser cutter.
On behalf of the Michigan Tech Open Source Hardware Enterprise, I would like to thank all of our sponsors, General Motors, Milwaukee, the MOST Research Group, the Michigan Tech Enterprise Program, Colormaster Incorporated, and ArcelorMittal. And more information about the enterprise itself, please go to our website by following the QR code on screen, or go to our Appropedia page that has more in-depth technical information on all of our projects we shared today. Thank you.